So, thank you for coming to see this talk. My name is Jakub Bokshansky. I work for NVIDIA. And my talk will be mostly about ray tracing, specifically about the SDK for ray tracing that we launched last year, which we call Kickstart RT. So let's see what that is about. The motivation for creating this SDK was that we wanted to create something that would help people embrace ray tracing easily. So lower the bar of entry, especially for people who don't have previous experience with ray tracing or not just ray tracing algorithms, but general with ray tracing pipeline of current APIs. We wanted to provide some most common effects like ray traced specular reflections, diffuse GI, shadows and ambient occlusion. And we wanted to make this as easy to use as possible. So of course, when we have the kind of solution where one solution fits all, there will be some disadvantages of using that. And the main disadvantage of this is that we use simplified lighting and scene representation. So you don't get as much visual fidelity as you would with the full-fledged native ray tracing solution. But again, the effort to integrate is much less than to integrate full ray tracing pipeline. And we also wanted to support all the main platforms. So this runs on Linux, ARM, and Windows. And we do support free APIs. We have Vulkan support, DX12, and also DX11, which is interesting because DX11, of course, doesn't have any ray tracing support, but we kind of plumbed it down through interop with DX12. So you need DX12 level hardware. The ray tracing runs in DX12, but you can talk to it via DX11. And to make it even easier to use for everybody, this is open source. So you can go on GitHub and find it. It's released under MIT license, so we can modify it, basically use it in many ways you want. But I have to say, it comes with the integrated Denoiser, which is NRD, that's also an NVIDIA SDK. And that is using a different license, so that's not MIT, just be aware that if you use this, make sure the licensing works for you. So now I've explained kind of what it does. Why would you use this SDK instead of doing it yourself, like everything from scratch? Because that's, of course, relatively a lot of work. And even if you make like basics work, then going all the way to make everything work in a typical 3D application is a huge amount of work. For example, first of the things you will need to do is to build BVH acceleration structures for your geometry. Now that seems like it's one API call plus some memory allocations, but in big 3D applications, you will have to soon start supporting things like streaming geometry in and out, releasing obsolete geometry, updating BVHs to support animations, which maybe you cannot do that every frame. Now we have to think about how to throttle BVH updates, distribute them between frames, and of course, instancing and managing memory for BVH structures. So then the second step you will have to take is to rewrite all your materials and lighting into ray tracing pipeline. Now, the most difficult thing here is that if your application doesn't have bindless support, then this becomes very difficult. Because if you think about tracing rays randomly in a scene, then you start in some pixel, you hit something, and the neighboring pixel hits something completely different piece of geometry, and you need to load different texture, different lights, basically in the same compute path. So you need to bind all of your geometry and materials and lights into single dispatch. Or you can start doing some clever things to work around it, and then it becomes really difficult. So what we've seen with applications where we integrated ray tracing is that if you have many shader variants, then mapping these into ray tracing pipeline gets very complicated, because if you just map it one-to-one to hit shaders, then you end up with possibly tens of thousands of hit shaders if you just map it one-to-one. Or you will end up with some complicated Uber shader, which is very slow, and you need to start optimizing that. And also, if your application uses non-PBR materials and lighting, meaning they don't behave as real light in real world, then ray tracing mostly works, but you can come into some weird situations where you do multiple bounces of light and the light starts accumulating and it gets brighter the more it bounces around and so on. And then one of the biggest engineering and research tasks is denoising. So ray tracing is inherently noisy. You get noisy reflections, noisy GI, noisy shadows. You need to denoise that. And that's just a whole different topic. So with this Kickstart RT SDK, we handle these things internally. So BVH builds are handled internally completely. You just submit your geometry, and when it comes obsolete, you just mark it as not used anymore, and the SDK takes care of everything internally. We also handle lighting and denoising, but with some simplifications, which I'll get into soon. We have these 4 supported effects. So specular reflections, diffuse GI, ambient occlusion, and soft shadows. These are denoised images. Just to give you an idea what it looks like, I think it's pretty good for what this, for the low amount of effort it takes to integrate this SDK. Now we have some shots with and without Kickstart SDK. So this is without. Now I'll flick the image, and you can notice the reflections appeared, especially on the bottom. So let's go back once more. And that. So that's specular reflections. And now we have a screenshot with diffuse GI. So the typical sponsor scene, it's quite dark in the shadows, but now I'll turn Kickstart on. And it gets a lot brighter because we get indirect lighting from the diffuse GI pass. So how does it work? I was talking about simplifications that are taken. And the biggest thing is that instead of using lights and materials in the ray tracing pipeline, we use a thing we call the LightingCache, which you can imagine as the old school pre-baked lighting. So every surface on every geometry, we store lighting information about the light that is incident on it, and we use that for ray tracing. So the drawback is, of course, you need to fill this somehow. You need to generate that. We don't pre-bake it. It's not offline. It's completely created online by reusing the lighting from main rasterization pass. So basically, we fill this LightingCache by the main view. So you only get LightingCache filled for stuff that you looked at in the past, which is, of course, not excellent. That's mostly equivalent to screen space effects with some temporal accumulation. However, to work around this problem, we enable filling LightingCache from multiple views. So we can have one or more additional views, which are generated just either around the main camera, or if you know some walkthrough pass through the scene, then you can have second camera that's just walking through the scene, filling the light cache all the time. And now, third problem with this LightingCache is that if there's something specular in the scene, then of course the rasterizer is shading it for view direction of the camera. And now when we have secondary rays, you may see some reflection which wouldn't be there from that direction. So this is, again, a simplification that we took just to make it work as easy as possible. So when will you want to use this? So we were thinking that this can be a great prototyping tool for applications which may want to use ray tracing, but the engineering effort to do that is too much. And you want to see first, like, let's get an idea of what it might look like if we had ray tracing. You can integrate this, and then this is open source, so you can modify it to your liking by removing the LightingCache and doing proper materials and shading. And we were also thinking it can be great for games, especially older games without bindless support and DX11 titles, where this is certain screen space effects, but it doesn't require as much engineering effort as full ray tracing. And it's, of course, open source. So I believe personally that this can be a great learning tool for people who want to start doing ray tracing, but they don't know how, or they just want to see the results first and then start tinkering with the code like I do. So now let's take a look at some implementation details, how we actually did it. So this is an overview of what SDK does internally. So in this, I don't have a, yeah. So this first step is basically the user application has to submit geometry, meaning index and vertex buffers, and the SDK builds the BVH. Then the user application has to create the G buffer and shading, which it already has probably. Oh. And the SDK internally creates this LightingCache that I talked about. And then in the third step, you just have to decide what ray tracing effects you want from the SDK. You tell it, I want diffuse GI plus some shadows, and it gives you the output buffers. So the LightingCache, let's first talk about how that is filled. So we start by casting primary rays for the camera to figure out which entry in the LightingCache corresponds to a given pixel. And we use the same shading routine, same hit shader for secondary rays, because we only need to figure out entry in the tile cache for each ray to fill it or to read from it. We call this the light injection pass. And in order to make it more temporally stable, we apply some temporal accumulation. So we have this exponential moving average thing, which user has to fine tune to get acceptable temporal stability and not too much of a temporal lag. And we have two types of LightingCache. So first, we simply call regular tiles. That's this thing with quadrilaterals. It's very simple. It's easy to address. There is no indirection. You don't need any edge tables or anything. It's just calculated using barycentric coordinates. And the second is mesh colors, which is much nicer. You can actually interpolate between these circles, so we get very smooth lighting, but it requires indirection. So let's first take a look at this basic LightingCache. We think it's better when you have a lot of elongated triangles, because you can subdivide each triangle into n by m patches. You can have elongated triangles with relatively equally sized patches. But because we cannot interpolate between individual cache entries or circles or whatever you want to call it, then in the mirror reflections, you can actually see the tile cache. Probably doesn't show very well on this, but let me flick it back and forth. So this is for mesh colors, where we interpolate between them. And this is the all tile cache. It's quite subtle, but it's noticeable. So let's talk about mesh colors. This is based on a very nice article by Cem Yüksel. And you can only have n by n patches, so each triangle is subdivided equally. So when you have elongated triangles, it might not be the best. But it of course has a huge advantage that we can interpolate between neighboring cells. So we get smooth lighting instead. So we have some debug views to visualize these tile cache. These red points are LightingCache entries on the inside of the triangle. Green ones are on the edge. And basically, the user has to decide how big are these patches going to be, because large, of course, you get more. With large amount of these circles, it eats a lot of memory, but you get a lot more fidelity. So if you have something like perfect mirrors in your scene, then you want to see some texture details in the reflection, then you need to use really fine LightingCache. And these debug views can help to find out the correct setting. Now I talked about this bilinear interpolation between circles of mesh colors. So this slide shows what I mean. So on the left, the interpolation is turned off. You can clearly see these hexagons, which correspond to circles. On the right, with interpolation, the lighting is really smooth. So you can see even some detail on these tiles, I think, on the wall. And yes, here's again the comparison of regular tiles and mesh colors. Now, one of the last things about LightingCache I want to talk about is people ask, what about alpha testing? So as you can see, we didn't solve it in the SDK at the moment, but it should be quite straightforward to implement. So the idea is that everything that hasn't been seen yet, so tile cache starts empty, and then when you walk around, you discover what's in it, what should be in it. So we should start with everything fully transparent. We would add one visibility bit to each entry, and then when it's seen by something, then it must be opaque, so we mark it as opaque. That's the idea how this could work, but it's not implemented yet, and we consider it to be future work at the moment. So now let's talk a little bit about this problem that we fill LightingCache by main rasterization pass. So if you don't have a second view, then you can only use ray tracing for stuff that you look at or you've seen in the short past. So we recommend having at least one more additional view that can be in, let's say, quarter resolution, so it can be rasterized very fast. And we had good results with the orbiting camera around the main player. So there was one more camera which was rotating around player, and it was also rotating around its own axis randomly. And basically, if you have a setup like this, then in 1 second, if your application is running at 60 FPS, then you get 60 additional views to fill LightingCache with surrounding data. And that's usually enough to make it look believable and much better than the screen space techniques. And of course, dynamic scenes just work. If you don't set this temporal accumulation to be super conservative, then dynamic scenes just work out of the box with this approach. So a little bit more details about the effects this is producing. So Diffuse GI is just one bounce, and it's Lambertian or Disney diffuse, so the simplest diffused BRDFs you can think of. Why is it one bounce? Well, because our tile cache doesn't have any material information, so we cannot do another bounce because we don't have material data to figure out the next redirection. But if you inject this ray trace diffuse GI into your main rasterization pass, then the feedback happens and you get multiple bounces over time. So it's not completely like single bounce lighting. Then for the specular reflections, we use a typical GGX model, which is based on roughness. Now this is an interesting thing because we completely disregard what the application is using, but since we don't have any material data in the SDK, that's like the only choice, so we chose the most common thing. It's open source again, so you can change this to whatever you need or like. Ambient occlusion is really simple. You can only adjust the range. And I would argue that if you have diffuse GI, you don't need ambient occlusion, but maybe for some artistic purposes or experimentation, it's there. And for shadows, we have support for directional lights, point lights, and spotlights, so the most basic types. But it does soft shadows, so you can get very nice soft shadows from this SDK. The Denoiser, I already mentioned, it's our NRD, which stands for NVIDIA Real-Time Denoisers. So I think this is really the killer feature of the SDK, because denoising is very hard to implement correctly and fine-tune for application. And in this SDK, you can just turn it on. If you agree with the license, which is different, there's for the rest of the SDK. Yeah, this image shows the direct output of the ray tracer, which is noisy, and then denoised image is very usable. So if you were to integrate this, so let's talk a little bit about this. This is cross API and cross platform SDK. So there have to be some abstractions over basic concepts that we use. If you were to integrate this into your application, you will mostly work with 3 basic objects. One is the execution context, which you can think of as a global state of the SDK. You initialize this with your Vulkan device or DX12 device, and it holds a global state of the SDK, and you use it as a handle to call all the other functions. Then we have what we call task container. This is essentially wrapper around the Vulkan command buffer or DX12, command list. So the SDK will want to do some work on your command buffer. And you need to provide it to the SDK so that it can fill it and return it back to you. And then the third kind of object you will deal with is a render task. So this is really a high-level task like build BVH from this geometry, or give me ray traced reflections, or denoise this buffer. And since there are 4 effects and the optional denoiser and BVH builds, you can really implement this to your liking. Like, you don't need to use all the effects. You can just cherry pick what you want. You build your render tasks, and the SDK injects them on the task container. So important thing, the SDK doesn't own or create any threads. So it should be thread safe, but any threading you need to implement yourself on the application side. That's on the CPU side and on the GPU side. So there is some room for parallelism. I'll get into that a bit later. So once you've integrated these basics, your application basically calls some functions to prepare render tasks that you want. Then you give it a command buffer to fill. It returns the command buffer back to the application, and you need to execute it. And then you need to signal that command buffer has been finished. Because, for example, there are some dependencies between these render tasks. You cannot start tracing rays until the BVH is fully built, so there has to be some feedback from the application saying, like, this command buffer has been already executed, or it reached a certain point where you can start tracing rays. Now, since this is a Vulkan conference, I decided to talk a little bit about how we achieved free API support. So from the user point of view, we have this piece of code on the right. It's very simple. So first you define what API you want to use. Then you include our header file, and then you just use function calls in the proper namespace. So in this case, it's Vulkan. And you don't really have to care about anything else. Inside, in the SDK side, we have been thinking about how to approach this best. So there are some open source abstractions over most known APIs, which we could have used. But we realized that we are only using very, very small subset of Vulkan and DX12 and 11. So if you think about it, we're just injecting some compute dispatches on the command buffer and possibly binding some resources. We don't have to deal with swap chains and presence and anything like that. So we decided to write our own custom abstraction layer, which is implemented really, really simply. We just have, if you're using DX12, there's a bunch of DX12 code. If you're using Vulkan, there's equivalent Vulkan code. And the whole thing is in these 2 files, if you want to take a look. I think it's about 1,000 lines of code to support all 3 APIs, which I think is very small. So let's now take a look at the overview of the frame. Once you've integrated Kickstart into your application, you'll see these new render passes. So the orange ones are to prepare the LightingCache memory and to build BVH. And these can happen in async compute in parallel while your original application, which is green, does something, probably rasterization and other effects. Then you have these new Kickstart passes, which are violet. So direct light injection, that's just filling the LightingCache. Then your ray traced effects that you chose and denoising. And then there is final render pass again in your application where you compose the final image together from all the components. Let's now quickly take a look at the performance. This has been measured on some game, which was non-trivial. It was a really recent and complicated game. And the whole Kickstart thing runs in about 3.5 milliseconds in 1440p on the mid-tier GPU, the RTX 3070. So it's really fast. Now the problem with ray tracing is that it consumes a lot of memory. So in the same application, it took almost 3 gigabytes of extra memory just to support Kickstart, and there's a breakdown. Like LightingCache is almost 1 gigabyte, which I think is a lot, but you can fine-tune that based on the fidelity you want. Then BLS and TLS, that's of course dependent on how much geometry you want. And Denoiser and other are just Denoiser and other. So some fine-tuning tips. If you decide to give it a try, we will be very happy. And so probably the first thing you will run into is that you cannot have all of your geometry in the BVHs. So we need to think about what you really want in the BVH, probably just something which is near player, like 20 meters or 40 meters. And maybe you will not be able to build every BVH every frame. So what we typically do is we only update BVHs after animation in like every second frame or every third frame. So what does this mean in practice? The secondary rays which do reflections and diffuse GI will not see updated geometry to the latest animation. That may be a problem if you have some perfect mirrors in the scene. It will be a bit jittery, or it may not be a problem at all because all your reflections are glossy and you wouldn't see a difference anyway. So the second, the tile cache size, I've talked about it. So depending on fidelity, you decide what works for you. Then you can try checkerboard rendering. So that's basically doing all the ray traced effects in half resolution, and you can temporarily resolve that to full resolution. So in 2 frames, you get you get the same image with slight delay, but you're only tracing half of the rays, which can be a huge time saving depending on the GPU that it's running. And then I'm not sure how many people are familiar with the difference between trace ray and ray query. All right. So relatively a lot. So one is not better than the other generally. For an application like this, you have to try it in your specific application to see what is faster. So basically, trace ray executes this state machine with closest hit shaders, any hit shaders, miss shaders, and it gives you, well, it doesn't give you any result. You just trace ray and it executes your code. While ray query, it's literally just finds the intersection and tells you intersection is here, now do whatever you want with this information. So to summarize, this is open source SDK with relatively easy access to ray tracing for older titles or people who want to start doing ray tracing and don't have previous experience. All ray tracing tasks are handled internally, so you don't need any ray tracing knowledge to get started. And it gives you common effects like GI reflections and shadows. So I thank you for your attention. And if you have any questions, feel free to ask. Okay. Yes.
I think you mentioned it, but I'm not sure. How do you understand the material roughness that you show in these reflections? And right on the floor level, like what reflection, but no reflection from the base?
Yeah, so the question is, what's the roughness to calculate the reflections based on, right? So we have this GGX-based specular BRDF implemented, and the roughness is basically alpha parameter corresponding to that.
Where do you get it?
Well, games do use it quite a lot. It's artist driven.
Does that come from the GBuffer?
Yes, from the GBuffer. Yeah. Yes.
I don't know if you mentioned, but the MIT license versus the Denoiser license. Can you somehow have it optionally included to the user, or can't you?
Yeah, so the Denoiser is optional, and it comes with a different license because it was released much earlier.
Okay, so you can use the MIT license.
Yes, you can only use the part which is MIT. You don't need to use that. You don't even actually download the repository if you don't want to. Yeah?
Did I get right that the shadows actually bypass the surface cache and only use like VDH because you only need to like complete this?
Yes, exactly. So the shadows don't really need any tile cache data to work. It doesn't use any lighting. So if you really want just shadows, you don't even need to bother with that part. Yeah. Yep.
How about shaders in the library?
Yeah, so shaders are built during build time, and I think they are embedded in the Windows DLL. So they are essentially loaded from the library as a resource, and it's the same on Linux. That's even simpler to do. But you can modify shaders. It's open source, so you can play with this as much as you want. Any more questions, please? All right. Well, thank you. One more question, or
Yeah.
yeah.
The signaling when is there any support for semaphores?
Yeah, so the question is about these tickets that we need to signal back to the SDK. The task is finished. I don't remember, actually. I think it's a fence. You just signal on a fence that it's done. But honestly, I don't remember. I'm sorry. It's been a while. Okay, well, thank you.